Hi everyone, welcome to today's video. So this is my topic number 17, and for topic number 17 I have chosen effect of dilution on conductance. This is from electrochemistry chapter and which is from physical chemistry. Okay, fine. So I previously uploaded one video from conductance, okay, on conductance. So if you have not watched that video, please watch that video first because that concept is needed here. Okay. So the concept of how in that video I have shown to you from Ohm's law how we came to know the conductance, what is the conductivity of the solution, and the molar conductance, equivalent conductance, how they are related. Okay, so these kind of things are there, and also their units. Very important thing is their units. Okay, so if you know this much, you can understand today's topic also. Okay, this will be based on some theory portions are there, I will say, and also some mathematical portion is there. But when we think about theory portion, we think that that will be boring, right? But here it is not. I will make sure that you can understand it in a easy way. I will teach you in a easy way and with the main important thing only, which are needed for understanding this topic. Okay. So let's start with today's topic, and please make patience and carefully watch that video. Listen to the lecture carefully. Okay. I hope you will enjoy this session. Let's start then. So first, I will be talking about the electrolytes. What are electrolytes? We know, right? The compound which are actually giving ions when we took it in a solution, right? But there are two kinds of electrolytes. One is strong, another one is weak. How can we say one is strong and one is weak? Which is defining this? The degree of dissociation. Okay. So here, for strong electrolyte, we know the examples are salts. When we mix it in a water, let's say in water, the ions are actually generated in a faster way. But we are not saying faster, slower, or anything. The dissociation should be checked. Okay. So the dissociation means the reactant is converting to ions, right? So 100% dissociation means almost uh, every reactant molecules are reacted. Okay, reactant and forms the solvated, actually solvated and forms the ion. Okay, and alpha is the degree of dissociation. How can we define alpha? Let's say from reactant to product is forming, so alpha will be product by reactant taken. Okay, product formed by reactant taken, that will be the alpha value. Okay, so this is the degree of dissociation. So when we took weak electrolyte, what will be the difference? Alpha will be less than 1, means alpha is product by reactant, right? So product by reactant, so not much product is there. We know for a ratio, okay, when it will be less than 1, when R is greater than P, right? Reactant is more than product. So not much product has been formed from reactant. So it is very less for weak electrolyte. The value is very less actually. Okay, we can't sometimes ignore the value while calculation. Okay, so here, for example, let's say CCOOH. Okay, NH4OH. This is weak base. This is weak acid. So these kind of examples are there for weak electrolytes. Fine. So with dilution, what happened to the alpha value? We will see. So here, dilution means what? Dilution means, let's say we have taken here. Okay. So let's say this is some V liter. Okay. And 10 molecules of NaCl present. Fine. Now we have added V dash amount of volume. Now the total volume means V total is V plus V dash, and total molecules of NaCl is same like previously, N dash equal to N equal to 10. Previously, let's say 10 N was there. So N equal to N dash equal to 10. So the number of molecules are same, but volume is increasing. That means what is happening? Here, what is happening? Only volume is increasing means, so that will be now the total volume. So the space, the total solution, the space is actually increases, which only affects uh, the distance between ions. Okay, for strong electrolytes, for any electrolytes actually, but strong electrolytes has only that effect. Okay, so with dilution, what can be the alpha value of that strong electrolyte? After dilution, what will be the alpha value? So we know alpha value is what? Alpha value is product by reactant, right? So here 100% dissociation happens. Means if we take 100 molecule of reactant and 100 molecule of product has been formed, alpha will be 1. So now what is in the solution? What is left? Only product is there, right? Right? The ions are there only. So after dilution, what will happen? They just only have the bigger space to move. Okay, nothing much. So alpha value will never change because it is the highest value. Okay, so that is the thing. So with dilution, alpha remains same for strong electrolytes, but for weak electrolytes, what will happen? For weak electrolytes, actually, the alpha value increases. Alpha, the dissociation increases. Okay, so yes, that is the thing here. So when we when put the volume of water, let's say, when we add, that time alpha value will increase. That means the dissociation will increase. Now alpha dash will be greater than alpha, right? So we know that yes, dissociation will be different now. Fine. But why we are reading this? Why? We have to relate somehow, right? So before that, before relating it with anything, before that, we have to understand that Oswald dilution law for weak electrolytes. This is valid only for weak electrolytes. What is this? Just now we have read about, right? That with decrease in concentration means we have read that increase in dilution or increase in volume. Increasing of volume means the decreasing of concentration, because concentration is what? Mole per liter or the moles per volume. Now volume has increased and mole is same. Mole is mole, but L has now greater value, L plus L dash. So this one has more value in this side. Denominator value is more. So the concentration C dash will be obviously less than C, right? So that is the thing here. Decreasing concentration and increasing dilution, what will happen? The alpha value increases. This we can explain with Oswald dilution law. Oswald only he has taken the weak electrolytes and proves that this actually happens. How? Let's say we have taken one weak electrolyte, the acetic acid, the dissociation of acetic acid. Fine. At t equal to 0 seconds, let's say C amount of C mole we can take, or C concentration. The we have taken that of the reactant. At T0, there will be the products will be 0, the ions. And T equal to T equilibrium, the C will be C minus C alpha. So we have taken alpha as degree of dissociation, and this is for, we know alpha is what? Product by reactant, right? So this is, we have taken, let's say C amount of mole is taken. Okay. If C moles are actually taken, that time P by C will be there, right? So P will be C alpha. Understood? P will be means product will be C alpha. So here C alpha and C alpha. Okay. So how much amount of reactant left? C minus C alpha. C was there minus C alpha, right? You have understood this part, right? Now what is happening is that we know equilibrium constant is what? Sorry, no negative sign is there. Sorry. So equilibrium constant means the product or products, the concentration of product by concentration of reactant. Okay, in equilibrium. So at T equal to T equilibrium, the product concentrations are C alpha and C alpha multiplied obviously and divided by concentration of reactant. So C will be cut out and C alpha square 1 minus alpha, right? And we know we have taken the weak electrolyte. So for weak electrolyte case, what is happening is that the alpha value is very less. The dissociation of the weak electrolyte is very less, right? So we can take 1 minus alpha, 1, we can ignore this, right? As it is very, very small than 1. Okay, we can take approximately this value as 1. Now if we put the value, the K alpha will be C alpha square, K equilibrium will be, now alpha is K equilibrium by C, root over. Okay, fine. Now, okay, we got this, but how can we prove that this part? How can we prove this statement? See, here concentration term is there. So here what we are doing? We are decreasing concentration. So let's say when we are decreasing concentration, that time denominator decreases, means the whole ratio value will increase and so alpha value will increase. Simple. So when C is decreases, alpha value is increased, which is proved, which we talked about actually. So this comes up from Oswald dilution law. Fine. Now why we are reading this kind of things? Okay, the knowledge of this is fine, but there shall be some reason, right? Why we are reading or how. So these kind of concepts are important to understand the effect of dilution on conductance and conductivity. See, we were talking about the dissociation of the electrolytes. Now we are relating that with the conductance and conductivity, the effect of dilution. See how why chemistry is saying like magic this is. So that part, the degree of dissociation is actually affecting in the conductance. Let's see how. Okay, fine. So now for strong electrolytes, let's say. So we know for strong electrolytes, after dilution, when we add water or add any solvent, okay, when you add any solvent, there is effect is only, let's say this was the volume. Now after addition of volume of water, let's say the volume is this much. So now if 10 molecule is there, so now again 10 molecule is there, but they got bigger space. So ions are actually moving inside the solution, right? They have charge also. So they got the higher space to move in, and so that their velocity actually increases, or mobility, ionic mobility increases. Fine. This effect is only there and nothing effect is on the degree of dissociation. Okay, fine. So with dilution, force of attraction between ion decreases. Okay, space is increases means their mobility increases and the interionic attraction actually decreases because they are now in a space apart. So attraction will be more when they are close, right? So these kind of things are there. So force of attraction between ions actually first decreases. Speed of ion increases, force of attraction decreases. So what was happening? Let's say for the case of NaCl. So Na plus is attracting the Cl minus. Let's say they the Na plus actually hold the hand holds the hand of Cl minus. Okay. Now after dilution, what happens? The he can't now hold their the hand. Okay. So they are far apart now. So attraction is less, right? So any ion can now sit in front or near Na plus, right? So these things are there. So only effect is this, right? But how it affects on conductance? See how it affects on conductance. So conductance is what? Conductance is the conductance. It is the opposite of resistance 1 by R, which means it is the ease of carrying the electricity or the movement of electricity. R is what? R actually resistance what? It restricts the movement of electricity, and conductance is for a specific compound. Let's say conductance is there ease of movement of ions. Okay, so movement of ions when increases, the conductance will obviously increase. So they can carry more and more charge now. So conductance will be obviously increase. So there is the increase in conductance, right? So in the case of strong electrolyte, conductance increases. How? How? Because after increasing in volume, force of attraction decreases and speed of ion increases. Fine. Let's come for now weak electrolytes where alpha is less, dissociation is less. So how it affects? So here in this case, we have previously in Oswald dilution law, we have told you after dilution, when V amount of volume is solvent is added, that time what will happen? Now degree of dissociation, alpha will increase. That means, let's say CH3 COO H was giving what? CH3 COO minus plus H plus, these two ions. When their degree of dissociation will increase, that means the product, because alpha is product by reactant, so product will increase. The product means the ionic conversion, this conversion, this to this conversion will increase. That means the number of ions now increases. Alpha value increases means number of value ions now increases, which actually uh, so conductance is what? Conductance is the ease of carrying the electricity or the power of the carrying of electricity. Okay, so the power will increase when more amount of ions are there, because ions are only carrying the electricity, right? So that is the thing here. So conductance will increase with dilution, dissociation increase, number of ion will increase, and conductance increases. Okay, fine. So other factors are also there, but here main important thing is the dissociation increases. Okay. Now coming to the variation of conductivity with dilution. Conductivity means kappa, right? So kappa, we know that this is kappa, this is conductance, and this is A by S. Okay. So the conductance of one semi-cube solution when A is 1 and A is 1. So the conductance of one semi-cube solution is called the conductivity, right? So if let's say a solution of, let's say a liter solution we have taken and many ions are there. So we will not talk about how many ions in the solution and like that. So conductivity will be when we took inside the solution 1 liter part, that the 1 liter part, how many ions are there? That will be the kappa, or their conductance, obviously. How many ions, not how many ions, how many ions are there, and how they are showing, or what value of conductance they are showing. Okay, that will be the value of kappa. Fine. So now when we dilute any solution, what will happen after dilution? Let's just now understand that what will happen. Volume will obviously increase, V will increase, V dash will be greater than V. Fine. But number of moles are same, right? N dash will be equal to N, because we are not adding the molecules or ions. Fine. So what will be now? So when we now find out the conductance of one semi-cube solution, let's just not talk about conductance. Let's just talk about that the number of ions in one semi-cube solution, which was here, will it be the same in here? The conductance of one semi-cube solution, not conductance, sorry, the number of ions in one semi-cube. Okay, so here if you see, the number of ions will be more, because here volume is more, so ions are far apart. Okay, so that doesn't mean that they will that means that they will not be in they can, some of they can be in 1 liter, but not everyone, not every ions, right? Because now volume is increases, ions will the ionic movement is increasing increases, right? And let's forget about that. So the 1 liter, let's say V amount of let's say, okay, in 1 liter, how many number of molecules was there in 1 liter? N by V, right? And here let's say number of ions, N dash by V dash, the new moles and new volume, but the moles are same. Moles of or number of ions are same, so it will be N again, and V dash will be V dash. So if we compare this N by V and N by V dash, which one is more? Which one is more? We know here V dash is greater than V, right? So here denominator is more than this one. So the N by V dash will be less than N by V. Fine. So the number of moles or number of ions in one semi-Q solution will be more in the first case, before dilution case, than the after dilution case, right? And the conductance is actually depends on the what? The conductance is proportional to the number of ions, obviously. Number of ions, which means the increasing amount of ions will increase the conductance. So here the number of ions actually decreases after dilution. So the conductance value will be, or this one will decrease, right? So with dilution, number of ions per unit volume decreases, the N by V dash, that is decreases, and conductivity decreases. Fine. I hope you have understood by seeing these two examples. Now the effect of dilution in molar conductance. Okay, that's lambda m. Okay, so the molar conductance and dilution. So molar conductance, we know that it is the multiplication of K and Km. Fine. So two factors are here. So with dilution, we have told that K value. So we have to see the two factors, right? Because with dilution, what is happening? So volume increases. So obviously molar volume will be increased. So after dilution, volume will be obviously increased, right? So Vm will increase. So Vm dash is now greater than Vm. Fine. And kappa, what will be the kappa value after dilution? So we just talk about this, that the kappa value will what? Will decrease when we diluted the solution, because the number of ions in one semi-Q or 1 liter solution, 1 unit solution, let's say, is decreases. That's why kappa value decreases. So here the thing is that the molar conductance, which has the two parts like kappa and Vm. So Vm will increase when the solution is diluted and K is decreases. So which means by seeing that equation only, we can assume, if we assume, so the thing is that it is decreases and it is increases, so overall the effect will be same. So we must be thinking that, we should think that delta m dash will be equal to delta m, means the delta m dash will be the same. But theoretically we can say that, but practically that is not the case. So let's just find out what is the practical case. So this is the, on dilution, the conductivity decreases, means kappa value decreases, and volume increases, the Vm increases. The combined effect is, let's say, that should be that no effect in delta m, lambda m, but the experimentally it is find out that the decrease in conductivity is less than the increase in volume. Means the increase of volume, that effect is more than the decrease in kappa. So this effect is more. Means with this effect, what was happening? The increasing was there, right? With dilution, it was increases. It increases, right? So as the volume part has the now the volume part is now the main factor here. So as volume is increasing, so delta M value will increase, right? So now overall molar conductance actually increases, like Gm. Fine, that was very interesting, right? And same will be true for lambda equilibrium also, means equivalent conductance. Okay, and it is true for both strong and weak electrolyte. Okay, both strong and weak electrolyte shows the same thing. Fine. Now the molar conductance and dilution again for strong electrolyte. Okay, so there we will study one graph that how actually molar conductance with dilution they actually change. So we previously told that molar conductance and the molar conductance of strong and weak electrolyte for both cases actually the molar conductance is it increases with dilution, right? We have just read about. So it will increase obviously, but what will be the graph look like? The graph will look like this for strong electrolyte. When we place, try to draw the graph of delta M versus root C. Root C means the concentration effect only. So a linear increase is seen with dilution, obviously, with dilution. Or decrease in concentration. That means in this way, the increase can be seen. It approaches a limiting value when concentration tends to zero or infinite dilution. You see, there will be dot 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 because concentration zero is difficult to attain. So that's why dot dot sign is there. But we can extrapolate by when we got some data and we can extrapolate that linear graph, we can find out that line when we extrapolate, we can find out that limiting delta M value when C goes to 0. Okay, fine. What will be we call? So the limiting value of molar conductance at infinite dilution is called lambda M0. Okay. So now how actually this graph actually came? We know that strong electrolyte case or weak electrolyte, with dilution molar conductance increases. But how it increases? From where the linear equation actually came? So with these actually we can explain. Delta M equal to delta M0 minus A into root C. A is constant like Mx and C is X obviously. This is C, constant value. Okay, fine. So slope is negative, you can see. So here slope is negative minus. Fine. So when we took this and plot that, we will got this one, right? So we could plot in linear fashion for strong electrolyte because here only one factor was there, that is the while dilution happens, the movement of ions or mobility will increase and the attraction decreases. The same thing. So one factor was there, that's why the curve was or the graph was simple. Okay. Let's just find out for the case of weak electrolyte. So before that, there is another thing. If you see here that lambda M by lambda M0 is alpha. Again alpha came. So lambda M means the conductivity, molar conductivity at any point by lambda M0 means molar conductivity at infinite dilution will be equal to alpha, that degree of dissociation. Okay, we are relating that. See how we are relating the things. Okay, so this is very important formula and questions are actually came from this this formula. Okay, please try to remember that one. Now for weak electrolyte, fine. The same thing is for weak electrolyte, the same formula actually, but not the same thing. So with dilution, what happens? The decrease of dissociation, the degree of dissociation will increase, right? and also number of ions also increases, like the every electrolyte, like strong electrolyte case also. Okay, no, for strong electrolyte only their velocity will increase. Okay, so here degree of dissociation increases, fine, number of ions increases, fine, and their speed also increases, or mobility also increases, fine. So various things are actually playing a role here when we are diluting in the case of weak electrolyte. So that's why the graph here will be like this. There will be a drastic increase. It's seen with dilution. Drastic increase means like this way, and it doesn't approach a limiting value. Okay, so when we try to make the c equal to 0 also, or very close to c equal to 0, it will be like this. It will be parallel to y-axis. It becomes parallel to y-axis when we try to go towards the what? The limiting value. Okay. So in this case, most important thing, please listen carefully. The for the case of weak electrolyte, we can't find any limiting value delta lambda m0. We can never find out. Fine. So here the important thing is the graph. So combined graph, if you see, this is for strong electrolyte, which follows that this equation lambda m equal to lambda m0 minus a into root c. This equation it will follow. And for the case of weak electrolyte, various factors are there. Here only one factor was there. Here various factors are there. We have seen that points. So the graph will be look like this, and there will be a drastic change. Fine. And we can never find the limiting value for weak electrolyte, while we can find the limiting value for strong electrolyte. Okay. Now the Kolar law. So what is this? From where this law actually came? Suddenly Kolar law. What does it mean? So I have previously again and again told you that the limiting value of the weak electrolyte we can never find out, because the graph when it goes to uh, never find out. So when in the graph when we try to go towards the c equal to 0, the graph will look like the parallel to y-axis. It will never uh, cut the y-axis. If we extrapolate also, we can never find the value. Okay, but by the Kolar's law, we can find out the with the by knowing the correct lambda m 0 values of strong electrolyte, or the ions, constituents ions of the particular weak electrolyte, we can know about the delta m0 for electrolyte. Fine. So the Kolar's law is important for that point of view. But let's from there actually Kolar's law came, but the statement is the limiting molar conductivity of any electrolyte, limiting molar conductivity equal to the summation of individual contribution of cation and anion. Okay, this is not only for weak electrolyte or something like that. It is valid for all, weak or strong, valid for all. Okay, so this is actually, sorry, this is the Kolar's law. This is the Kolar's law. Okay, so let's say we take an example for HCl. So the limiting molar conductivity of HCl will be their constituent ions, the summation of the individual contribution of cation and anion towards the conductivity. So the conductivity, limiting molar conductivity of H plus limiting molar conductivity of Cl minus. That will be the limiting molar conductance of that HCl. Fine. Now, if we take another example also, like NH4Cl, let's say. So for NH4Cl, what will happen? NH4Cl, let's say this one. So it will, NH4Cl will break like NH4 plus and Cl minus, right? So NH4Cl, the molar conductivity, limiting molar conductivity of the overall NH4Cl will be limiting molar conductivity of NH4 plus limiting molar conductivity of Cl minus. Okay, so like this way we can represent that. Fine. But for weak electrolyte, the limiting molar conductivity, how we can find? Let's just take that. How can we get the limiting conductance value for weak electrolyte? That is a big question. Let's see in the next slide. So let's say the three equations are given. This is for one strong electrolyte, that NH4Cl, which is equal to the summation of that constituent ions. Okay, let's take a weak electrolyte case also. Let's say NH4OH. Okay, NH4OH. It will be also the same. NH4OH equal to lambda 0 of NH4 plus and lambda 0 of OH minus. This will be simply this. But we don't know that value. We can actually find out directly that lambda 0 NH4 OH value, and also these values NH4 plus or OH minus, these values we can find out by from the strong electrolyte case. Okay, so from that only we can determine the molar conductance of weak electrolyte. How? Let's say this is one equation, this is two, this is for HCl, this three is for H2. Okay, and we have to find out the lambda 0 for NH4OH. Fine. So how can we do this? Okay, we know that lambda 0 for NH4OH will be equal to, according to the Kohlrausch law, it will be equal to NH4 plus lambda 0 of OH minus. Now see, we got these values. Okay, like this is, let's say, X, this value is Y, this value is Z. Fine. So now how can we determine the value of this with respect to X, Y and Z? Let's see that. Okay, so lambda 0 of NH4H equal to this. Fine. So how can we get, using these values, how can we get that NH4 plus OH minus? See that. So NH4 plus will be added. Okay, so let's just take this NH4 plus this is there with this NH4 plus, so we have to take that. Fine. Now H plus and Cl minus, is it there? No, right? No H plus and Cl minus we can see. So will be minus lambda 0 H plus minus lambda 0 of Cl minus. Now H plus and OH minus. Okay, OH minus value we need here, so keep that for plus H plus lambda 0 of OH minus. Fine. Now see what will be. Now we can count H plus and H plus minus, we can cut this and this. Okay. Now what is left? Lambda 0 NH4 plus lambda 0 of OH minus. Right? We need this only. So this will be lambda 0 of NH4 OH. So what will be the value of this? Now what will be the value of this? The value will be, now let's say this was X. So we have taken the summation, we have taken this as this X. So Y was, we have taken negative, so not plus, this will be X negative Y, and this is the Z we have taken as summation, right? So plus Z. So this value will be X minus Y plus Z. Fine. When we solve a few questions, you will understand in a better way. So let's see some examples. So this actually came in CSIR-NET December 2011. So the molar conductivities are defined as dilution, delta M0. Sometimes this delta M0 actually it is used for the this molecule. So when we took molecule, their conductivity is actually uh, represent as this, and for the ions, actually lambda values are this kind. Okay. So delta M0 for NH4, Na2SO4, K2SO4, KCl, ACl, ACO, Na, various values are actually given. But why? What we need, we have to see that first. The delta M0 for formic acid we need. So first write what we need. So formic acid we know HCOOH, right? After dissociation it will form H plus and HCO minus, right? These two ions. So delta, here we have to write delta. So delta 0M of HCOOH will be equal to lambda 0M of H plus lambda M0 of HCO minus. This we need, these two values actually we need. Okay, HCOOH. These two values we need, but how can we get these two values? Let's just see how this, what is given. Na2SO4 is given. How it can actually ionize? Okay, let's just. It will be HCOOH, right? Okay, fine. So these we need. Okay. Now see what is given. So Na2SO4, how it ionized actually? 2Na plus SO4, 2 minus. Okay. So the delta M0 of Na2SO4 will be simply 2 will be multiplied with the lambda 0M of Na plus value. Okay, 2 will be multiplied because 2 positive ions, 2 sodium ions are there. Fine. And SO4 minus is 1. So lambda M0 SO4 2 minus. Fine. This is the equation number 1. Or we can write the value also. The value is 260. It is equal to 260. Okay, this is equal to. Now forget about this one. The second one. Second one is K2SO4. Again same way, right? 2K plus will be there, plus SO4 2 minus will be there, right? So the delta M0 of K2SO4 will be again like same way, 2 lambda M0 of K plus lambda M0 of SO4 2 minus. Fine. Now third one is, okay, this value is equal to 308. Forget about the unit right now. All has same unit. So that's forget about now. Forget about this right now. So 3 is KCl. KCl and HCl also there. Okay. So for KCl, K plus and Cl minus. So it will be delta M0 of KCl will be M0 of K plus lambda M0 of Cl. Fine. For HCl also HCl. Okay, it will be equal to now. Will be now. Okay. This will be equal to what? 150. Now for HCl, delta M0 of HCl equal to lambda M0 of H plus lambda M0 of Cl minus. It will be equal to what? 426. Now the last one. What? HCOONA. HCO minus plus Na plus. So lambda HCONA is lambda m0 ACO minus plus lambda Na plus 0. Okay, and this value is what? 105. Okay, so these are the values: 105 here, 426, 150, 308. The individual values are like this: 1, 2, 3, 4, 5. 5 values are there, right? 1, 2, 3, 4, 5. 5 values are there. Fine now. So now what will happen is that, so we have to find out the how of by summing few values or subtracting few values, we have to anyway find out the H plus and H plus ACO minus value. Fine. So let's just now see that in which equation has H plus and ACO minus. We just first add those two equations. Okay. So H plus has the HCl has H plus, right? Na2 is to 4, K2 is to 4. So HCl, this one, it has this 4 and this is 6. So fourth one has H plus. Okay. So we'll simply, let's take another slide. All are gone. I'm so sorry. So again I have to write. Okay. So what was the thing here? Tell me simply. Simply it was 1 was delta 0 m Na2SO4 will be equal to delta m0 of 2 into delta m0 of Na plus delta m0 of SO4. Fine. Second was K2SO4. Delta m0 of K2SO4 is 2 delta m0 of K plus delta, sorry, lambda m0 of SO4 2 minus. Fine. Third one is for KCl, I think. Yes, KCl. KCl is the lambda m0 of K plus lambda m0 of Cl minus. The same is for HCl. Delta m0 of HCl will be equal to lambda m0 of H plus lambda m0 of Cl minus. Okay, fifth, the last one is delta m0 of HCONA is equal to lambda m0 of HCO minus plus lambda m0 of Na plus. Okay, so these are the fifth equation. The value of each is 260, 308, 150, 426, 105. Fine. And in the question, what is actually we have to find out? The delta m0 for formic acid ACOOH, which is equal to lambda m0 of HCO minus plus lambda m0 of H plus. Fine. So in which equation we get that we have to find these two values, right? So in which equation the lambda f ACO minus is there and H plus is there, we just simply first add sum that two equation. Okay. So somehow summation and subtraction, after summation and subtraction, we need to find out this sum value. Okay. So that we get the this value. Okay, first we see in which equation ACO minus is there. In which equation? The fifth equation, right? Here see ACO minus is there, and where H plus is the delta M H plus, it is here 4. So first 4 plus 5. So see after when we add 4 plus 5, what will happen? So delta M 0 H plus obviously will be there, plus obviously with it delta M 0 CL minus is there, so we have to take it, and lambda M 0 of ACO minus, which we need, and with this lambda M 0 of Na plus is also there, we have to take it, right? And the value will be 446 plus 105. Okay, so what we get actually from here, nothing will be cut down. We got this and this, but here is CL minus and Na plus is also there. So now we have to cut somehow the Na plus and Cl minus from this equation. How can we cut that? We have to find out where Cl minus is there and Na plus is there, and we have just simply have to subtract that equation from this equation. This sixth equation. Okay. So where is Cl minus? Let's just find out here in the KCl. HCl we have taken, right? We don't have to take this again because 2H plus will be there now. When we add this equation, there will be 2H plus. So we don't add this. We have to add HCl, this one. This has Cl minus, not add, we have to subtract. Okay. If we subtract with this, what will happen? H plus and H plus will cut out. But we want that H plus in that term is needed. Okay. So now let's say from 6 we are subtracting the 3. Now what will happen? Delta M0 is plus delta M0 Cl minus plus delta M0 ACO minus plus delta M0 Na plus is there. Now we are subtracting with HCl. Delta M0 of A plus minus delta M0 of Cl minus. Fine. And the values will be of this will be 246, 105 minus HCl value is 150. Let's just come to the next slide. So now it will be, so that was there, right? These actually, we can copy this one. A smaller version. Okay, that will be very helpful. Okay, now, okay, again. So we got this value now, this one. Okay, so what is actually cutting out? So let's just see, Cl minus and Cl minus will be cut out. And now what is left, I am writing here, delta M0 of H plus delta Cl is not here now, delta M0 of, lambda M0 of HCAA minus plus lambda M0 of Na plus one thing is there, lambda M0 of minus, this is minus, lambda M0 of K plus. See, this is what the value will be. (426) plus 105 plus minus 150. The value will be now 380. 381. But we don't get the value of the what we need, because again Na plus and K plus is there. So we have to remove that. We have to somehow subtract the Na plus value, and we have to somehow uh, add some K plus value so that it will be subtracted. Okay. Now see, this is Na2SO4, this is K2SO4, where Na plus and K plus is there, but multiplied into 2. Sorry, something is going on here. So here, okay, fine, this is fine. So now what will happen? Na plus and K plus has, so first equation has Na plus and second equation has K plus, but multiplied into 2. So we need only delta m0 Na plus. Here 2 delta m0 Na plus is there. So we have to divide by 2. This let's say 1 divided by 2. Okay, we have to add this, we have to subtract this, as Na plus we have plus here, so we have to negatively sum it. So minus I by 2, 1 by 2, and plus, because K plus is here, negative, after negative K plus is there, so we have to add the K plus value, and here is again 2 is multiplied, so the second equation by 2. So we have to this one with this. We have to add this one. So now what will happen? Delta m0 of each class plus delta m0 of HCO minus plus delta m0 of Na plus minus delta m0 for K plus. It was there, and again we are taking negative first equation, which is delta m0 of Na plus minus, again SO4 minus, but 1 by 2 into delta m0 of SO4 minus 2 minus, right? And again we are adding what? 2 equation number 2, but we are dividing also with 2. So delta m0 of K plus, it will be again plus 1 by 2 into delta m0 of SO4 2 minus, right? And the right hand side will be what? It was 381. Now we are subtracting the equation 1 by 2 actually. So 368 by 2, and we are adding second equation, and after dividing by 2. So 308 by 2. This will be the answer. But how I am saying that it is the answer? See, Na plus and Na plus will be gone. K plus and K plus will be gone. Plus minus. And minus half delta m0 of SO4 2 minus, and plus half delta m0 of SO4 2 minus. This will be also gone. So what is left? This one, which is actually delta m0 value of HCOH, formic acid, which will be equal to now, so 268 by 2 plus 308 by 2, now sorry, 381 minus 268 by 2 plus 308 by 2. Okay, so answer is this one. Okay, you can solve this. The B is, I think, the answer. Okay, so if I understood this was a lengthy problem, but I am solving like that way that you have to understand each and every time. But when you practice it more, after seeing that only, you can understood that which you have to subtract and which you have to sum. Okay, by seeing that only. So you know HCO minus is there, you have to add it. H plus is there, you have to add these two. And now Cl minus we should remove. This will be subtracted. And for K plus and Na plus, we have to subtract these two, and after dividing by 2. Okay, this we can simply just, after putting all the value, we can just simply calculate. Okay, so this will not take much time, but I am teaching you, so that's my goal is I have to make you understand properly, so that's why it takes time. Okay. Now the second question is, in the graph below, the correct option according to the Cholera's law. Okay, in the Cholera's law, what we have seen, that lambda m or molar conductance versus root C is plotted, and for the strong electrolyte we could get this kind of graph, and for the weak electrolyte we get this kind of electrolyte graph, right? This will be the for strong weak, and this is for strong. Fine. In the question, what is given? These various graphs are there, and the correct option according to the Cholera's law is, okay, A is a weak electrolyte, B is a strong electrolyte. A is a strong electrolyte, B is weak electrolyte. Okay, fine. C is strong electrolyte and B is weak electrolyte. C is okay. So see, for the strong electrolyte case, we know that the slope will be negative, right? So we have to find out in which cases the slope is actually negative. So for the D and C, but C is actually like this. Here one point is there, and again at the same point one graph is like this. So obviously D will be the strong electrolyte. Okay. Their option is, I think, C will be there. So C is strong electrolyte, like this way, and because for the strong electrolyte, the lambda m0 is much more. So we know that this kind of graph is seen for the weak electrolyte, but here nothing. This kind of graph is not there. Only the negative slope and positive slope graphs are there. So we know that when we diluting the solution or decreasing the concentration of the solution, the lambda m value will increase. So in these two cases only we can find that. Okay. So let's just forget about A and B. Okay. A and B we have to cut out. So A and B options are only consisting of A and B graphs. Okay. We have to cut these two, and we have to see in between these two. And for the strong electrolyte case, so here the slopes are actually seems like same, but for the strong electrolyte case, we know that it actually touches the y-axis, right? So it will touch the y-axis, and yes, that is the thing here. So it touches the y-axis, that means C will be the strong electrolyte. That is for sure. And here with this, D is electrolyte, weak electrolyte, it is written. So it will be weak electrolyte. Okay. So C will be the correct answer. So I am so the question I have shown to you various kind of questions. So if you solve from the Cholera's law, actually many questions are coming in the exam. So if you solve it more, practice it more, you will be understanding in a better way. So thank you so much for watching till now, and hope you have understood this. And if you have any doubt in some portion, because sometimes it is a bit difficult to remember, and it can actually be a bit confused about how the concentration is affecting molar conductance and the conductivity in a different manner. So you can be confused. So don't worry, just write in a comment section. In the comment section, I will be happy to help you. Okay. So thank you so much. See you in the next session.